Hey everyone, this week's paper is towards universal fake image detectors that generalize across generative models. I'm trying to get the field, a scope of the field for fake image detectors and what are the new methodologies each research paper implements. So came across this paper, just trying to see what all new things they have come up with. So let's go ahead. Just to make a couple of things very clear. So I think the title suggests they generalize across generative models. So they are going for generalization, not just the detection. All right, let's go for it. In this work, we show that the existing paradigm, which consists of the training of the deep network for real versus fake classification, fails to detect fake images from the newer breeds of generative models. So this is why they are doing it. Upon analysis, this is the probable cause. Upon analysis, we find that the resulting classifiers is asymmetrically tuned to detect patterns that make the images fake. So there are a couple of keywords in here. Asymmetrically tuned. Okay. The real class becomes a sync class holding anything that is not fake, including generated images from the models not accessible. Okay, so what they are saying, like during the training you have the real class and fake class. So when it starts generalizing for image detection, so if the model is not trained on that data, then they are terming it as a sync class, which is anything and everything that the model hasn't seen. So it kind of starts putting it into a real class that is not a fake class. So basically that's what they are coming up with, the new terminologies. Building upon this discovery, we've proposed to perform real versus fake classification without learning, that is using a feature space not explicitly trained to distinguish real and fake images. We use the nearest neighbors and linear probing as instantiation for this idea. So a couple of things in here, we'll get to know more about this once we go through the paper and what they are coming up with. And they are primarily targeting these two. So it has a nearest neighbors and a linear probing for instantiation of this idea. When given access to the feature space of the large pretrained vision language model, the very simple baseline of nearest neighbor classification has surprisingly a good generalization ability in detecting fake images from a wide variety of generative models. For example, it improves upon state-of-the-art by 15 mean average precisions and 25.9 on ACC when tested on unseen diffusion and autoregressive models. So they're seeing some good results here with their given this thing. All right, as you all know, I skipped through the intro, I skipped through the related work, and let's go ahead with the preliminaries. So given a test image, the task is to classify whether it is captured naturally using camera or whether it is synthesized by a generative model. We first discuss the existing paradigm for this task and analysis of which leads to our own proposed solution. So now they are setting up the problem. So let's go ahead what they have done. The authors trained a neural network F for the task of a binary real and fake classification using images associated with the one generative model. So they are saying like mostly it's just one generative model that is trained to identify fake versus real. They train program on 20 different object categories of LSUN and generate 18k fake images per category. In total, the real versus fake training data sets consists about 720k images, 360k in real, 360k in fake. They choose ResNet 50 pretrained on ImageNet as a fake image classification network and replace fully connected layers to train the network for real and fake classification using binary cross entropy, of course. During training and intricate data augmentation schemes involving Gaussian blur, JPEG compressions. By the way, JPEG and Gaussian blur, most of the images for real and fake, if you use these augmentations, these two specifically, they tend to make it more robust. It has been proven, and it kind of came up in other images, other research papers as well. Once trained, yeah, so which is empirically shown to be the critical generalization. Yep, that's what I said. Once trained, the network is used to evaluate real versus fake from the other generative model, for example, Big GAN. So you're training on ProGAN with the backbone of ResNet 50 and changing the fully connected layer, but you're evaluating on Big GAN images, whether it is class conditional generated images or corresponding real images. Gets classified correctly, that is with similarly each generative model has a test set with the equal number of real images and a fake images associated with it. So this is what has been traditionally followed. That's what they're saying. Now with the 3.2, what they are proposing is the analysis of why prior work fails to generalize. So this is like what they think why it fails to generalize across unseen data, unseen GANs, and unseen image forgeries that are coming up every now and then. So we start by studying the ability of this network, which is trained to distinguish ProGAN fake images from the real images, to detect generated images from unseen methods. In table 1, we report the accuracy of classifying the real versus fake images associated with the different families of generative models. As was pointed out in this research paper, they're saying when the target model belongs to a same breed of generative model used for training real versus fake classifier, that is GAN, the network shows good overall generalizability in classifying images. For example, if the data is trained on all the GANs, then it will easily generalize on all the GAN fake images from the same category, right? Now, there are two ways in which classifier achieve chance performance when the test set has an equal number of real and fake images. So when the validation data, when the testing data has equal number of real and fake images, it can do either of these two. So one, a random prediction on each test. So it starts predicting just random label, starts assigning all the random fake or real images label. And the second one is the same class prediction for all the test images. So it starts giving out the same labels for all the unseen data. From table 1, we find that from diffusion models, the classifier works in a later way. The classifying almost all images as real, regardless whether they are real or not. So it kind of fails in a way. They're kind of over exaggerating now, overwriting all this document. Given this, it seems F has learned an asymmetric separation of real and fake classes, where for any images from either LDM, unseen fake, or LAION, unseen real, it has a tendency to disproportionately output one class, real or fake, over another. Okay. So basically, again, they are reiterating why it fails if anything other than GAN is to be tested, and which has the similar sort of distribution of the real versus fake. To further study this unseen phenomenon, we visualize the feature space used by F for classification. So now they're visualizing the feature space for F for classification. We consider 4 image distributions, FGAN consisting of fake images generated by ProGAN, RGAN consisting of real images used to train ProGAN, so FGAN, RGAN, F diffusion consisting of the fake images generated by the latent diffusion models. R diffusion is the real images, I believe, used for training diffusion models. And the real versus fake classifier is trained on 1 and 2. For each, we obtain their corresponding feature representations using the penultimate layer of F, okay, and plot them using TSNE. So basically, they are just now identifying how it behaves in feature space. I mean, if the GAN is actually able to segregate those two distributions, or it's just making stuff up, which they have seen it's already making stuff up. So the first thing we notice that F indeed does is not treat real and fake classes equally. In the learned feature space of F, the 4-image distribution organize themselves into 2 noticeable clusters. The first cluster is F GAN, which is the fake of GAN, pink, and the another one is the amalgamation of the remaining. So basically, it's just putting all the fake data on one side and rest, which it hasn't seen, which is all real and all that, into one cluster. And this is in figure number 2. So let's just take a quick look at figure number 2. I think it's all the way here. So there you go. As you see, this is fake and rest. It has seen whatever it hasn't seen, it's already clustering like that, which is horrible. Let's see. In other words, F can easily distinguish fake GAN from the other 3, but the learned real class does not seem to have any properties of its own, but rather used by F to form sync class. So this is what they mean. So whatever it hasn't seen, it's kind of putting everything in the same bucket. The second thing we notice that the cluster surrounding the learned fake class is very condensed compared to the one surrounding the learned real class. So what they're saying is much more denser than if you had to take individually. So say either you pick up on green or yellows, they are much less denser than the pink one in here. Okay, compared to the one surrounding the learned real class, which is much more open. This indicates that F can detect common properties among images from FGAN with more ease than detecting the common properties from the images in RGAN. So now we know what exactly the sync class means, which basically means anything that is not the identifier detector is treating all the non-fake, whatever is real, whatever it hasn't seen, into same bucket. So it's kind of using it as a sync. If you're unsure about that prediction, just put it in that bucket, that sort of thing. Okay. But why is it that the property of F finds to be common among FGAN is usually for detecting the fake images from the other GAN models, but not for the detecting F diffusion? So now we are working on, if it is able to detect fake images from GAN, why it's failing on F of diffusion, so fake images of the diffusion models. In what way the fake images from the diffusion models are different from the GANs? These are the important questions. We investigate by visualizing the frequency spectra of the different distributions inspired by these resources. For each distribution, we start by performing the high-pass filtering, for which each image is for each image by subtracting from its median blurred image. Okay. We then take the average of the resulting high frequency components across 2000 images and compute the Fourier transform. Figure 3 shows this average frequency spectra for 4 fake domains and 1 real domain. Let's see what 3 is going for. So star GAN frequencies, cycle GAN frequencies, guided LDM, LAION. So first four are fake, and this is real. Let's see. There's very noticeable patterns over there, though. However, we see a distinct and repeated patterns in star GAN and cycle GAN. However, this pattern is missing from fake images from diffusion models and LDM, similar to the images from the real distribution. So while fake images from the diffusion models seem to have some sort of property of their own, so they are very different from GAN. GAN is kind of coming out with its own fingerprint sort of thing. Indicates that the property is not familiar with the similar nature of the one shared by GANs. Okay. Our hypothesis is that when F is learning to distinguish between fake GANs and real GANs, it latches on to the artifacts depicted, learning only to look for presence and absence of these patterns in the image. Since this is sufficient for it to reduce the training error, it largely ignores the learning of any other feature. So basically, it has just gotten smarter. For example, smooth edges pertaining to the real class. This in turn results in a skewed decision boundary, where the fake image from the diffusion model lacking the GAN's fingerprints ends up being classified as real. So this is what they have come up with. This is what their hypothesis is, which is kind of consistent with all the other papers that I've read. Most of them extract these fingerprints and kind of start building a classifier based off of just those fingerprints. All right, number 4, the approach. So what they have done different now. We understood why it's behaving like that, where the error is coming from. Now let's see how they have tackled it. If learning a neural network F is not an ideal way to separate real R and fake F classes, what should we do? The key, we believe, is that the classification process should happen in the feature space, which has not been learned to separate images from the real classes, from two classes. This might ensure that the features are not biased to recognize patterns from the one class disproportionately better than the other class. So now they are choosing this feature place. Let's go choice of feature space. As an initial idea, we might not want to learn any features. Can we simply perform the classification in pixel space? This would not work, as the pixel space would not capture any meaningful information beyond point-to-point pixel correspondences. So any classification decision of the image should be made after it has been mapped into some other feature space. So what they are kind of reinforcing on that point, that they would rather want to go ahead with the feature space. But again, there are some ways to identify on pixel domains as well. So basically what they do is just subtract these fingerprints and only put the high bilateral high pass filters just to get the pixel ideas and start performing it on that. Anyway, coming back to this paper. So this feature space produced by a network is denoted by phi. Should have some desirable quantities. So what are the qualities they are desiring? Let's see. The first phi should have been exposed to a large number of images, which is fair. Since we hope to design a general purpose fake image detector, its functioning should be consistent for a wide variety of real and fake images. This call for feature space of phi to be heavily populated with different kind of images so that any new test image is known how to embed it properly. Second, it would be beneficial if phi, while being general overall, can also capture low level details of an image. This is because differences between real and fake image arise particularly at the low level details. To satisfy these requirements, let me let's see what do they mean by low level. We'll get to know more about that. To satisfy these requirements, we consider leveraging a large network trained on a huge amount of data as possible candidate to produce phi. In particular, we choose variant of the vision transformer because it has trained on more data, and it is trained on a task of image language alignment, CLIP. CLIP VIT is trained on extraordinarily large amount of data, about 400 million images, text pairs, so it satisfies the first requirement of the sufficient data exposure. Additionally, VIT L14 has a smaller starting patch size, 14 cross 14, compared to the other VIT variants. We believe it can also aid in modeling the low-level image details needed for the real versus fake classification. All right, hence all of our main experiment, we use the last layer of CLIP VIT L14's visual encoder. Okay, that makes sense. The overall approach can be formalized in the following way. We assume the access to images associated with a single generative model, ProGAN, which is the same constraint as in that particular resource, are going from 1 to n, fake images going from 1 to n, denoted the real and fake classes represented, each corresponding to n images. So both of, again, they both have taken the same amount of data for the real and fake. D is the unification of both, which denotes overall training set. We investigate two simple classification methods, the nearest neighbors and a linear probing. Importantly, both methods utilize a feature space that is entirely untrained for real classification. Nearest neighbors. Given the pre-trained CLIP VIT visual encoder, we use its final layer phi to map the entire training data into their feature representations of 768 dimensions. The resulting feature bank is phi bank, which is phi of real and phi of fake, and it should have during the test time, an image x is first mapped to its feature representation phi x. Using the cosine distance as a metric d, we find its nearest neighbor to both the real phi r and phi f feature banks. Okay, that's neat. And then we are basically making out the prediction. So it's as simple as just the nearest neighbors. Just grab a couple of neighbors, see the cosine distance, and associate 1 or 0, depending on your terminology. So instead of making it in the image space or frequency domain, what they are doing is basically just doing it in the feature space itself. All right. Smaller distance of those two. Yeah, typical nearest neighbor task. Now let's see the linear classification. We take the pre-trained CLIP VIT encoder, add a single linear layer with a sigmoid activation on top of it, and train only the new classification layer phi for binary real or class, and using the binary cross entropy. So this is another way of just making it. Either you do nearest neighbor, or you can just do a simple linear classification with one layer for binary cross entropy. Now let's look at the experiments. Well, actually, let me just jump a little ahead and see the results. So for the nearest classification, it's kind of surprisingly doing okay with 1, 2, 3, and oops, too big. Yep, it's doing okay. Frequency space still does better on cycle GAN. They do better in big GAN. Style GAN, still blur plus JPEG is doing better. Okay, here again frequency, star and big GAN frequency domains. Okay, this is doing better on deepfakes. SITD SANs, I think VIT clip is doing better. SANs, they are doing better. CRN, again, blur plus JPEG at 0.5 is doing better. Just the trained neural nets, and MLE is doing better for blur plus JPEG. Overall, they are doing pretty okay. Otherwise, even this one is still okay. Dolly, they are doing better. And overall the mean average precision is overall high. So that's what they were saying in the beginning. All right, let's see what did they have to say. Generalization average precision AP of the different methods used for real and fake. So this is the average precisions. Model outside the GAN column can be considered to be generalizing domain, since pro-GAN data is being used in training data set. The improvements using the fixed clip feature backbone over the best performing baselines train rate is particularly noticeable. So they are just saying like this is overall better because it's kind of adding up 19.49 mean average precisions than most. And for this one, I think analogous results for table 2, where we use the classification accuracy to compare the methods. So on top, it was mean average precision. This is overall classification accuracy. And again, they are saying overall they are doing better. Generalized ability of feature backbone can be significant gain with accuracy. So they're seeing about 50 to 30% increase over the baselines. This is great. All right, so this was the overall picture, and now they are just experimenting like an ablation study on network architecture and pre-training data sets overall. So you basically get the idea of where they are coming from, what exactly they are planning on doing. If anybody is interested in this paper, I would encourage them to go with as per their speeds on how this idea is there and how they are trying and what they are getting as a result. So thank you so very much for watching. I'm sure this was just like a quick glance through of this research paper. There's quite a bit there. Mostly that's how I read the papers. I usually go with the abstract, the data, whys and hows of their idea and the conclusions. I mean, there is a lot that could be done. Again, getting the unseen data all the time is impossible, because every now and then some new GAN or stable diffusion or some methodology is coming up. So I didn't actually go ahead and read this paper in entirety, but I generally got the gist of what this paper is trying to do. If this particular paper interests you, go ahead and maybe just download a copy of your own. I'll link it in the description, and just follow it through at your pace, and whatever the sessions I've missed, it's all yours. And I'll see you guys next week. Thanks.